Hello again. We've got another problem to work on today, and this one is how to draw a load shear moment diagram for a beam with pin supports. Now, load shear moment diagrams are something we work with a lot, and they're very useful, but it takes a little bit of practice to learn how to draw one correctly, so that's what we're going to do today. I've got a simple beam here. It's 2 meters long, and there are supports at point A and point B, and those two supports are 1.5 meters apart. And there's a 1,000 Newton load vertically down on the right end. Now, to draw a load shear moment diagram from this, we need to know what all the support reactions are. And we need to know the vertical reaction at A and the vertical reaction at B. Now, there are pins here, so there theoretically could be horizontal reactions. We don't have any in this case. So, to get started, we're going to do the same thing we always do with strength of materials problems. We're going to draw a free body diagram and then solve equations of equilibrium. So let's start with the free body diagram of the beam right there. I've got the beam itself, and I'm going to put a 1,000 Newton load, which we know. Now, there's going to be vertical forces at point A and point B. I don't know what those are, and I don't know which direction they point, so I'm just going to make some assumptions. Looks to me like the force at B will probably be vertical, although we'll find out later. So I'm going to draw that in. I'm going to guess that the force at point A is down. So there we have it. There's our free body diagram. All right, so next step is equations of equilibrium. We're going to be able to write some of the moments equal 0 and some of the forces equal 0. But in order to do that, I have to have a coordinate system I want to use. I have to assign positive sign conventions. So I'm going to use these. Just like that. And this is one I use most of the time. Unless I have a pretty good reason, I'll always use that one. So let's start by writing the moments about point A. Now, I can write moments anywhere I want. If I happen to write them about point A, then the force at point A doesn't appear in the resulting equation because there's no moment arm. So if I write a moment about point A, FB is the only term that'll show up, so I'm going to have one equation and one unknown. That's a convenient way to do it. So let's do that. So the sum of the moments at point A equals 0, and we're going to start here. There's no moment due to force A because there's no moment arm. There's going to be a moment arm here of 1.5 meters, and because that force is vertical, it's going to try to make the beam rotate counterclockwise, giving me a positive moment. It agrees with my sign convention. So I'm going to write, well, I'm going to write this as 3 over 2 because it's a little more convenient. 3 over 2 meters, that's 1.5 meters. Times FB. I don't know what FB is yet, but I'll find out soon enough. The moment here is a 2 meters moment arm times 1,000 newtons down, and that's going to make the beam want to rotate that way. Excuse me. So that goes against my assumed positive sign convention. So 2 meters times 1,000 newtons. That's going to all equal 0. So I'm going to rearrange this just a little bit. 3 over 2 meters times FB equals 2,000 Newton meters. Well, the units cancel out, and if you work this out, FB is going to be 4,000 over 3 newtons. And I'm just going to leave it in that form right now because it's going to be convenient to work with that later. So let me write that over here. FB is 4,000 over 3 newtons. Okay, and because I have just a little bit of space to work with, I'm going to erase that. Okay, next thing to do here is I'm going to sum the forces in the vertical direction, which is the y direction. And let's see, I know FA, well, I'm assuming FA is down. I think it is, and we'll find out here in a minute. So minus FA plus FB minus 1,000 all has to equal 0. So let me just rearrange here a little bit. Okay, so FA equals FB minus 1,000 newtons. Well, I already know FB, so that's 4,000 newtons over 3 minus 1,000 newtons, and that's going to give me a result of 1,000 over 3 newtons. And since it's positive here, it means I've assumed the right direction there. So I'm going to write that in. Okay, I have all my support reactions, so the next step is to draw the load shear moment diagram. So I'm going to erase this, clear out a little bit of space, and I'm going to need to have 2 segments in my load shear moment diagram. I'm going to have the segment that goes from A to B and the segment that goes from B to the end. So let's just draw that out up front here. See if I can do this straight. It's hard to draw straight lines freehand, but there you go. That's not too bad. That'll work. So I'm going to start up here with the load. All right. Now I know the load at the end is up, and it's 1,000 over 3. And I know this one is down, and it's 4,000 over 3. And I know that one's down. I'm sorry, I got this wrong, don't I? There, that's better. And 1,000 newtons at the end. Okay, so that's correct now. I'll put my units in there. Always track your units. So there we go. I'm going to draw the shear now. And that's going to be in newtons. Okay, now the way this works is we're going to move from the left end to the right end of the beam, and we're simply going to change our height here every time we come across a force. So if I have 1,000 newtons over 3 down, I'm going to go 1,000 over 3 down, and I'm going to just move over to the right until I hit another force, which is going to be that one right there. I'm going to go up 4,000 over 3 from this point. This isn't going to be quite to scale, but it'll be pretty close. That is now going to be 1,000 newtons. Minus 1,000 over 3 plus 4,000 over 3 gives me 1,000 newtons. And I'm going to go down, back down another 1,000 newtons. So that's going to wind up right at the 0 axis again. This needs to wind up at 0. If it doesn't end at 0, something's wrong. So let me just cross-hatch this so we can see what we're doing. There we go. There's the shear portion of the diagram. Last part now. Let me actually write that a little lower. Moment in Newton meters. Let me get out of your way here so you can see that. Okay, last stop on our journey here is to put that right at the horizontal axis for the moment diagram there. Now, in order to find out where we're going to be on this axis, we need to find out the area here. The area here equals the height there. This is really an integral, but it's easier to talk in terms of area. So if I have negative 1,000 over 3 times this distance, which is 3 over 2 meters, okay, that area is going to be 1,000 over 3 times 3 over 2, and that turns out to be minus 500. So there's minus 500 Newton meters right there. Now I'm going to start at that point and end at that point. The next question is it going to be a straight line? Is it going to be a curve? What type of line gets me from there to there? Well, the height here equals the slope there. Since the height here is negative and constant, the slope here is going to be negative and constant. So it's going to look just like that. They even got a nice straight line. Now, I know we have to go from negative 500 Newton meters back to 0 because there's no moment at the end. So I can just, if I was really not interested in checking my results, I could just draw a line from there to there. But let's check our results. The height here is 1,000 newtons and the distance there is half a meter. So the area of that little crosshatch box is 500 Newton meters. And since this is positive, this is above the axis, that means the slope here is also going to be positive. Positive constant height, positive constant slope. Change in height here equals the area there. Area there is 500 Newton meters. Change in height here is 500 Newton meters. And I go right back to 0 where I need to be. So there you have it, one load shear moment diagram.